Okay, so today we're going to look at a chapter on prior, right? So before, like, some question would be like, how do you choose a prior, right? And how do you actually select a prior so that you get certain posterior? So there is actually a prior formulation where we can actually select or use a certain behavior from the prior so that we can actually get a certain posterior. Okay, and this is, if you've seen the examples that we have in the previous chapters, we can see that we have uh, the examples where we actually have the prior and the likelihood combined, and we get a nice posterior, which is like a known distribution. Okay, and usually the posterior will have the same family of distribution as the prior, and these are called conjugate prior, right? And the attraction is because they will actually result in a posterior which is known distribution. Okay, so this means that when you have a conjugate prior distribution, that means that the prior and the posterior will be from the same family. Okay, so in the definition says that if you have a prior distribution from a class pi, right, and this is it will form a conjugate family, right, if the posterior is also in the class pi for all y. So meaning that, right, this means that if your prior is from in your family of pi, this will imply that your posterior, right, your posterior will also be in the family of pi. Okay, so this means that you can actually choose a prior such that you will get certain posterior, and this will actually depend also on your likelihood. Okay, so if you how do you actually ensure that your prior will be the same, so your posterior will be in the same family as your prior? We have to look at the likelihood or the joint PDF of your data y. Okay, so if you look at your an example, you have your data distributed where your data y given theta is a Poisson and your parameter is theta. So theta is the mean of the Poisson. Okay, so the gamma is going to be the conjugate to the Poisson, meaning that gamma will be your prior, right? And we will see that your posterior will also be have a gamma distribution. Okay, so now you should be familiar with this already, right? So now we have to find your likelihood. So now we have your joint distribution, right, of your data. So you have your right, your PMF. Sorry, so you have yi, and this is from 1 to n, right? And then think from the previous example, we have shown this that we can have this joint PMF, actually because it's a discrete, right? Okay, and we to make it easier, we define your S as your sum of yi, I from 1 to n. Okay, so if you look at the likelihood, right, of the likelihood of theta given y, then you can see that because as I say, right, the likelihood is theta given y, so you can actually use simplify and choose all those the parameter involving theta only, because y is a constant. In this, for the likelihood, y is a constant, right? And then you have your prior, right? So because here gamma is conjugate to Poisson, so gamma, your prior will be gamma, right? So you can also, you can write the full PDF or you can write the proportional, right? So for example, you have, right, So for example, your theta has a gamma distribution with parameter A and B, right? So you can actually use anything, but here is A and B, right? So your posterior, right? Your posterior, if you multiply your likelihood with your prior, right? So you can see, right, it has the same form, right? Theta power something and exponential minus theta something. So yeah, that's a sign that, you know, they come from the same family, right? And then you have your exponential minus theta multiplied by some constant, right? So this is, if you look over here, this would be your gamma kernel, right? So if you have a gamma, kernel, then you mean gamma is, you know, some parameter, theta power some parameter, and then you have exponential power some constant minus your theta. Okay, so this is your gamma kernel. Okay, so if you look over here, right, so you look over here, this is theta power something also, right? And then you have exponential minus theta power something also. Okay, so this is where, you know, your posterior distribution of beta is actually gamma, right? So whenever they ask you to find the posterior, you have to state also the parameter. So it will be gamma with parameter S plus A and then N plus B. Okay, so again, right, take note, right, if they say what is the distribution, you cannot just state gamma, that's it, right? I mean, you can, but I mean, you will not get full mark. So you have to state the distribution with the parameter for that distribution, right? So in this case, is your alpha and beta. So your alpha is S plus A and your beta is N plus B. Okay, so we have shown, right? We have shown that gamma, therefore, right? Gamma is conjugate to Poisson. Conjugate. Poisson. Okay, right. So, right, so here, the interesting part here is actually, right, you have to find the likelihood from your joint PDF or PMF here, and then you have to have a prior. So again, you have to recognize the kernel of the distribution, right? And so it's a gamma. So this means that if your prior is from a gamma distribution, this will result in your posterior is also from the gamma distribution with different parameters. So you have to state the updated or the new parameters for your posterior. Okay, right. So here, right, so for our case, so we are going to look at conjugate families, right, where the likelihood can be expressed in terms of a sufficient statistic T. Okay, so this means that, and we recall that if you have a sufficient statistic, then we can write the likelihood in terms of a function. So this means that your likelihood is only a function of your T and theta only. So meaning that if you have your likelihood is theta given y, then the y can be written as a function, the y can be written as a function t. Okay, that's it. I mean, the y does not exist anywhere, y is only in t. So you can actually rewrite your likelihood in this form. Okay, this means that then your t is a sufficient statistic. So if you were to use this part and rewrite your likelihood in this function g, then your posterior can also be rewritten in this function g, meaning that it's going to be your g t theta minus your prior p theta. Okay, which is your likelihood multiplied by your prior. Okay, then, right. So now you're going to look more into the details of the exponential family, right? So if you have a exponential family f, right, meaning that your PDF or PMF can be rewritten in this form, right, which is a function of y, function of theta, right, and an exponential function of phi theta times uyi. Okay, meaning that phi is a function of theta and u is a function of yi. Okay, and if y is exchangeable, right, then the likelihood can be rewritten into this form, which is your g theta power n times exponential times of, which is a function of theta and y. So t now is your sufficient statistic, right? And the sufficient statistic is actually the sum of your u of your uyi from here. So it's a sum of uyi here from 1 to n, because your data is from 1 to n. Okay, and as I said, right, again, you want to choose the conjugate prior, so that you get the prior, so the posterior has the same family as the prior. Then the easiest way is you can choose the prior which has the same form as the likelihood, right? So if you compare your prior with the likelihood here, then you have a function of theta, and then you have the exponential v theta also. But then you don't have, because your prior does not have the data, so you have any v, so v might be some some constant. Okay, of course, this is in general, right? So if you change your eta and your v, then you will rest the moments of the prior. Okay, so if we were to multiply your prior with the likelihood, right, and to check whether what is the distribution of your posterior, so you can see that, right, if you multiply your likelihood, so this is your likelihood and this is your prior, right, you can see that it's going to be a function, your g theta power some of the constant, some rewritten or new constant, and then your v dash is going to be v plus your sufficiency ty, right? So this means that your prior has the same form as so your posterior has the same form as the prior, so it is actually, the prior is a conjugate. Okay, right. Then, okay, so this means that, as long as you can write the likelihood in the form of this exponential family, then it will be easier to actually choose a conjugate prior. Right? So then we're going to look at your y is exponential, right? And then we're going to see that the gamma distribution is a conjugate for your lambda, okay, or conjugate for the exponential actually. Okay, right. So again, it's always the step where you can't escape, right? So this is where you have to practice a lot. So you have your data is exponential. Okay, then you have your joint PDF. It's always easier if you write your joint PDF first, right? So this is it's PDF, and then you multiply by n, then you have your joint PDF, right? So I just summarize it. So you have your S here. Okay, so this is actually your joint PDF, right? So if we were to compare this with your exponential family, right? So then we have your G, your function of your parameter, but now you have this lambda. So your G lambda is lambda, right? And then the exponential phi lambda, so you have phi lambda is actually minus lambda. Okay, and your sufficient statistic is actually your S. Okay, So meaning that if you have your function, then you have to recognize where is your g, right? Where is your phi, and where is your ti? Okay, based on the exponential family form, right? Okay, then so we're going to look at our prior. Okay, so but actually not if we don't look at our we're looking at our prior. So if you look at this likely join PDF, right? So if we were to choose like a a prior which is have a same form as your join PDF or your likelihood, right? So example, we have your, if you have your prior, so it will be log eta something. Then you have exponential. So this is your function for your prior, right? So if you use the G phi and the G and phi, which is from your likelihood, then we have no G lambda is lambda, so it's lambda power eta. Oh, okay. So sorry, this should be careful with the notation. This is actually eta, lambda power eta, and then we have exponential phi lambda is minus lambda, so we have minus lambda v, right? So if you look at this is actually the kernel of a gamma. So your lambda is actually has a gamma distribution with parameter this should be eta plus 1, and then we have v. Okay, because remember gamma, if you remember from the previous example, where is it? Right, if you remember the example, right, the gamma kernel, right, is parameter power a minus 1 exponential minus b theta, right? So this is the kernel of a gamma. Okay, so then we have, so now it's lambda, so here is actually plus 1 minus 1, right? And then we have lambda power minus v, exponential lambda power minus v. So then your a is actually eta plus 1, right? And then your b is actually v. Okay, so this is again a trick, right? So if you don't have 1, you just plus 1 minus 1, right? So then you actually get the form. So your a is eta plus 1. Okay, so you have lambda is actually gamma. So lambda actually has a gamma distribution with the parameters as given. Okay, right. So then if you were to find the posterior, theta given y, right, the posterior, if you multiply your likelihood and you have your likelihood multiplied by your prior, plus 1 minus 1 exponential b, right? Then you will have your lambda and plus 1 minus 1. Okay, so you can see, right, if you rewrite your posterior, then it also has a gamma kernel, right? You have a gamma kernel, then the lambda has a posterior distribution with gamma distribution, right? Then you have, okay, this is why you have to be careful with the notation is n plus theta plus 1, and then you have s plus v. Okay, so you can see over here, right, that your posterior is also gamma and your prior is also gamma. So it means that the gamma is conjugate to the lambda. Okay, in this case, it's actually the exponential distribution. Okay, and actually, what is interesting is actually if you think about the gamma, sorry, the exponential distribution, the sum of exponential is actually the sum of exponential random variables are actually gamma. Okay, that's why actually gamma, exponential and gamma, they are also from the same family. That's why the gamma is also conjugate for Poisson, and also gamma is also conjugate for exponential, right? But before, right, when you're using the Poisson, because they also have the same kernel, similar kernel, similar kernel, right? So then gamma will be conjugate for exponential and gamma will conjugate for Poisson. Okay, of course the difference is for Poisson your y is discrete, but for exponential your y is continuous. Okay, so just be careful about the data because the data might be discrete or continuous. So anyway, so this shows that you have a gamma distribution for your prior, then you also have a gamma distribution for your posterior. Okay. Okay, so the conjugate prior is one kind of the prior that you can use, which is also quite convenient, right? But there are actually other kinds of priors available, and one of them is called the reference priors, right? And reference is actually different from what we have learned because the conjugate is actually called an informative prior, right? Because informative prior means that we have a subjective belief about the parameters, so we put that as a distribution. Okay, so the conjugate prior is actually an informative prior. Okay, so another kind of prior is called the non-informative or reference prior, where we minimize the information in the prior, so as to let the data speak for themselves, supposedly. Okay, so this may be useful when you want to provide a baseline comparison. Okay, so means that in theory, right? In theory, the non-informative or reference prior actually contain no information, supposedly. I mean, in theory, that is what is supposed to be, right? The non-informative or reference is actually the will contain no information or no assumption about the prior. Okay, and sometimes also called something right. Okay, then how do you actually want to find an example of a reference prior or non-informative prior? So this you can use the fact that you want the prior to does not change much over the region of the likelihood and does not take very large values outside of the region. So this is the fact is called a locally uniform, right? So you want it to be uniform like a flat prior, but it's actually locally uniform, right? So for such prior, the posterior would be approximately, it will be proportional to your posterior, your posterior will be proportional to your joint PDF or your likelihood. Okay, so it's actually equal to standardized likelihood. Okay, so for example, right, so we have y is a binomial, right? Y is a binomial with parameter n and theta, right? So we have a uniform prior. So remember, right, y is your data, n is number of trials and theta is actually the probability. So this is important, right? Theta is between 0 and 1. Okay, so when you choose a prior for theta, it should be we have to look at the support of your theta. So here theta is between 0 and 1, so that's why we choose a uniform prior which is 1. So theta is uniform 0, 1 actually. Okay, right. Then if you have the likelihood, right, from the binomial, so this is from the binomial n theta, so this is the likelihood. And then if you multiply the likelihood with the prior, so you just like multiply likelihood with 1. So actually you have your posterior is actually proportional to your likelihood because you multiply by 1, right? Okay, and if you look over here, this is actually the kernel of a beta distribution. Okay, so you have theta y plus y minus y, right? And you have y minus theta n plus, sorry, n minus y plus y minus y plus 1 minus 1. Okay, so this is actually, right, even though basically the likelihood is actually from the binomial, but if you look at the posterior, okay, remember, right, because your theta must be, again, the theta must be between 0 and 1. Okay, so when you look at the, so you might think, oh, what's the difference, right? Because the likelihood is over from the data, from the joint PDF of the data, right? And the posterior is a probability, conditional probability for your theta, right? So your theta between 0 and 1, right? So multiply by 1, you get the same proportional, but this is actually, if you're referring to your theta, then it's going to be theta between 0 and 1. So the kernel is actually resembles the kernel of a beta distribution. So your parameter is actually beta y plus 1 and n minus y plus 1, because you add 1 minus 1 here, right? So you have the beta kernel. Okay, so here means that if you want to choose a locally uniform, that's why you choose a uniform 0, 1 prior for theta. Okay, so the other name for, for the reference or the from this prior is actually called the flat prior, right? Because when you have uniform, right, if you have your theta and 0, 1 here, it's actually a flat over 0, 1, right? So it's a flat prior. So this one is also called a flat prior. Okay. Then there are other consideration, right, when you choose a prior, right? One of them is actually, right, that the prior and posterior, as we learned last week, the prior and posterior are not invariant to transformation of the parameters. Okay, meaning that no, you have the Jacobian and things like that. So if we write, for example, if we have theta is the prior for, so okay, right. So if your theta is a uniform 0, 1, right? Theta is a uniform 0, 1, meaning that your p theta is 1, and then for your theta is between 0 and 1. If you have a transformation, meaning that you have your phi is equal to 1 over theta. Okay, so this is a transformation. Then uniform prior, meaning that you have theta uniform 0, 1. But if you use a transformation, phi is 1 over theta, then phi has this PDF, right? Phi actually have this PDF, right? So this imply, right, means that I actually say I know nothing about theta, right? Theta is a uniform 0, 1, meaning I have flat prior for theta. I assume I know nothing. Theta is flat. It's a non-informative, right? Distribution for theta. However, when I use a transformation, which is phi is 1 over theta, then it actually should be, right, if I were to know nothing about theta, then even if I change the parameterization, I transform it to phi, I should also know nothing about phi, supposedly, like. However, now if I use a phi is 1 over theta, then even if I use a flat prior for theta, but my phi now has a PDF, as a distribution. Because we have an informative prior for phi. but our theta is actually non-informative. Okay, so when we say we use a flat prior or uniform prior, it's actually not very consistent because it depends on the parameterization that we use, right? Is it theta or is it phi, right? If it's flat in a certain, if for theta, it's not flat for phi. Okay, so it depends on the function or the transformation that you use for your parameter. Okay, but obviously, even though this looks bad, right? But actually, that's not too bad in practice, because when you look at the prior, right, it does not change too quickly, right? And if you have a large enough data, then you can see that, even though you use a transformation from theta to phi, then it will not be that different. Okay, so meaning that, if you try to have a large enough data, right, it might not be bad, even though we use different, if we use transformation on your parameter. Okay, that is our hope, or our hope is like in practice, right? Because we cannot really in practice we cannot really control, right, our parameter. Okay. Oh, okay, right. So that is the non-informative or reference prior, right? Then we're going to look at something called a data translated likelihood, right? So if you have your data, sorry, you have your likelihood in the form of this function, meaning that you have G is a function of theta minus Ty, where Ty is a sufficient statistic, and this is called a data translated. Okay, because the data provides only information on the location of the likelihood function. Okay, meaning that your likelihood is a function, is only a function of theta minus Ty, where T is your sufficient statistic. Okay, so if you can find a scale of measurement, or maybe under some transformation, right, where the likelihood is data translated, then we should use a uniform prior on the scale. Okay, so because it becomes a non-informative prior. Okay, so if you look at example, right, how we actually want to find or use this data translated likelihood. So we're going to look at a normal, okay, a normal distribution Y, where you have parameter is, the mean is theta, which is unknown, and sigma square is known, right? So sigma square is constant, so it's not a parameter here. Okay, right. So here, right, so you have the likelihood, right, because I have the likelihood for normal, right? So now, by now you should be at least a bit familiar with like the kernel and things like that. So we have the kernel of normal, right? Like remember, likelihood has a n, is a from a joint PDF of n observations or n random variables, right? So you have the kernel of your normal distribution. So this is the likelihood is the normal, right? Then if we were to compare it, okay, I mean, if you look at the original, right? So this, not original, I mean, if you look at this is a kernel, but actually we can also rewrite it in the form of the normal, right? Which is theta minus y bar square. Okay, so if this is a kernel, right? But because it's not a kernel of the normal, right? We can also rewrite in the form of theta minus y bar square, right? So if you open the square, you got theta power 2, and then you have 2 theta y bar and plus y bar square, y bar square is a constant, right? So that's why it disappears in the original kernel. So you have this is the form, right? So if you compare it to that just now, the data translated likelihood, right? So you compared it to that function. So for a data translated likelihood, you must have a function of g theta minus dy, right? So if you look over here, right, this is the function is going to be your exponential, right? So this is function is your exponential, right? And then you have your theta here. This is your theta here, and then your sufficient statistic here is your mean here. Okay, so here means it will imply that your ty, your sufficient statistic is actually y bar. Okay, so if you compare that function, then here, then from the definition before, right, you have your, which mean this is actually a function of your x, right? So if I were to define my x, right, as theta minus ty, right, so my t is my sufficient statistic, ty is my y bar, then I can rewrite my likelihood into a function of x, right, rather than theta. So if I have my x given y, right, so it's actually a exponential minus n x bar over 2 sigma square, right, which is a function of x. Okay, right, so you can see over here, right, that now instead of a function of theta minus y bar is actually an x, right? So meaning it's actually your x is just one value, right? Because your sigma square is a constant. Okay, so it's just a function of x. Now it's a function of gx. Okay, and this means that since your sigma square is a constant, then your mean, sorry, your location, sorry, not location, your location, right, will actually change depending on the value of your x. Okay, or which also depend on your y bar. Okay, so meaning that if you were to have this likelihood, then the graph, right, would look like, a function of, for example, is x, right? Right, your graph would actually, if you have an x here, right, and then the graph, I mean the PDF or the shape will be the same, right? So meaning that they have the same shape, right? They might have the same shape, but depends on, so it's not x here, x should be here, right? And this is your L, the function of your x, right? Means that if you have different, the shape is the same, right? So it means it's a function of your x, the shape is the same, but depends on your center, it depends on your y bar, right? Which is your statistic, could be, the y bar, this one, or y bar, this one. So the center will move, but the shape of the likely of the L is the same. Okay, this is what it means by the location of the likelihood function. Location means the center, right? The center of the data of the likelihood function will move, but the shape of the likelihood itself is remain the same. And in this case, because we have sigma squared as a constant, then the shape is the variance is the same. Okay, the shape is the same. Just the center will move around depending on your sufficiency ty. Okay, then this will actually imply that you will actually use a improper prior distribution. So this is called a flat, uniform also, right? So we meaning that we will use theta, right? So this is actually called a flat prior because it's a uniform one, okay? But the thing here is is called improper prior. So we can see later on what does it mean by improper. And this is because your theta is actually from minus infinity to infinity, right? Because before if your theta is from 0 to 1, you have uniform 0, 1. So it's actually a proper PDF. But if I were to say theta has a flat prior or a reference prior of uniform is 1, right? But your theta is actually from minus infinity to infinity. So the range does not integrate to 1. Okay, that's why it's called improper prior. So anyway, if I were to use a flat prior for theta, which is also improper, okay, then my posterior will actually have, so my posterior will, if you look over here, right, then my posterior will also be proportional to my likelihood, right, multiplied by 1, because it's 1, right? Okay, and if you look at the kernel of the likelihood here, right, this is actually a normal kernel, right, for theta, right, and the mean is y bar and the variance is sigma square over n. So the posterior is actually normal, right, normal with mean y bar and variance sigma square over n. Okay, right. Okay, so take note, right, this means that if you can actually show that the likelihood is a data translated likelihood, meaning that it has this function theta, g is a function of theta minus ty, that means that it will suggest that you use a flat prior or uniform prior for your parameter. So that's why we actually use this one, meaning that this imply a data translated likelihood. So it will suggest you to use a flat prior for your theta. Okay, that's why you get 1 here. Okay, which is also improper prior, and then it will result in your posterior having a normal distribution. Okay, with the mean and variance as given. Okay, so the idea here is because, okay, why we suggest this is because we want to give the data the same shape, right? So we have so this is okay. Oh, okay, this is the graph I just draw, right? You have the same shape because you have the same variance, right? But it's only the shift in the location. Okay, so when you have a uniform prior, means that all locations are equally likely. That's why you imply. That's why here you imply that it's a flat prior, a uniform prior, which is 1, right? And because you are saying that all locations are equally likely, because uniform means that we have equal probability in distribution. Okay, right. Okay, right. So this is when you're looking at the data translated likelihood, right?
Excuse me.
Yes. Okay.
Yeah. So it seems to me that when you do that, it's like doing ML. That's your MLE, right? Basically, your S bar, your X bar has a distribution of the distribution that you get in the end. That's the same thing you get when you do a MLE of to find a parameter of
Yeah. Actually, okay. So this is okay. What happens here is actually it's not really wajib. I mean, this is more like a suggestion actually, right? It says that if you have this certain behavior, then they will suggest you use this sort of prior. This is actually a suggestion such that you get a nice posterior. So that is the exact suggestion. Okay, so example, if you have this behavior, you can, and you have a conjugate prior, then you have conjugate posterior, for example, right? If you use this flat prior, because you want to have non-informative, then you can use a flat prior or a reference prior. Or you have your data is data translated, then you can also use a flat prior. So it's more like a suggestion. That's why there's a lot of priors available actually. So it does not mean that you have to use them, right? It's more like a suggestion. So for like different cases of your data, or of your likelihood. Okay. Is it what you're asking, or
It
are you
seems to
asking?
me that when you when you use a uniform prior or a flat prior, that meaning
Yeah.
you assume your prior is all equally likely, then it's basically you get the same result that if you did MLE. You seem to find like data, right?
Okay. I understand. You mean yeah. If you use a flat prior means meaning if you look at the definition where oh no, sorry, I think it's over here. Right, yeah. So if you look at the flat prior, right, so you can see that the aim of the flat prior is you want to minimize the information in the prior. So to let the data speak for itself. Yeah. So basically we are letting the data speak for themselves. So the aim for the flat prior is actually we are actually basing it on our likelihood. Yes.
So it becomes back like frequentist
It's
approach.
intentional. It's intentional actually. Yes. That's why it's called a non-informative prior, because your prior is supposedly does not contain any information. That's why it's called a flat prior. So it's a kind of prior. So the thing here is just what I call it. It's just it's an option. So if you don't want your prior to be, if you want your data to have more say or to be more powerful, or to let the data speak for themselves only, then you can also use this called reference prior or non-informative prior. But if you want to use a different prior, you want to use a conjugate prior, also can. So as I say, it's a different option actually. Yeah. So so the flat prior really is intentional to let the equal proportional to your likelihood. Okay, so
Okay.
as you see here, it is intentional.
Yeah.
The
Okay.
posterior will be proportional to your likelihood. Yeah.
Okay. I get it. Okay. Thank you.
Okay. Right. Yeah. So you say, oh, so it is by intentional. By intention, it's not it's not because it's not a byproduct. It's the intention to get that. Okay. Right. What was I just now? Okay. Right. So if you have, I'm going to look at another example, right? So then we have now we have a normal, right? But now your mean is known, right? And then you have your variance, phi is unknown. So now your phi is your parameter. Your phi is unknown now, because all the while we look at our mean, but there are cases where no, your mean is known, but your variance is unknown. Okay, and then we're going to look at the transformation, right? This transformation, which is log 1/phi. Okay, so sometimes the thing here is, why do they use transformation is because the after transformation, then the behavior or the posterior for that parameter will have a certain special characteristic, and that's why we use the transformation. Okay, so for in this case we have your normal, right? So again we have our likelihood. Okay, so when you have your phi, your mu is known but your phi is unknown, then actually you will have this you can actually now you have to write it in the slightly different way, right? So you have this one, right? Because now your S square is actually very long. So Okay. Okay, so now, okay, the difference, right? Because why? Oh, it's still normal, right? But now, because the kernel is now different, because now mu is a constant and phi is your random variable. Okay, so if you look back at the previous example, right? So this is a normal kernel where your variance is known, is a constant, and theta, your mean, is unknown. So you can see over here, right? The constant in the mean, the variance, the value in the constant in the beginning, the sigma square, sorry, the sigma square here is a constant, so it disappear, right? So you only have theta here because here your theta is your parameter and your sigma square is a constant. Okay, but the same likelihood, if you want to look at when you simplify it, or when you make it into a kernel, so it depends on which one is your parameter, which one is a constant. Okay, so the same joint PDF can result in a different kernel. Okay, a kernel means whatever is constant, whatever is a parameter. So here theta is your parameter, sigma square is a constant. So you can see that anything with sigma square which is multiplied, this one or 2 pi whatever in the beginning, disappear because it's a constant. But now if your mu is a constant and your phi or your variance is the parameter, then the beginning one you cannot make it disappear, right? Which is your variance, square root of your variance. So this one you have your phi, this is your phi here, and now you have n something, and now if you have your mu here, this is a constant now. So this S square is actually a function of your data, which is now a constant. So that's why you can just write it as S square. S square is a function of your data and a constant mu, right? So it's S square there, right? So this is how you rewrite your likelihood. You join PDF or normal, but you change from the constant and the parameter. Depends on which one is constant, which one is parameter. Okay, so then you have this form for your phi, which is your variance. Okay, we don't use sigma square. Okay, so whenever one thing, right? Whenever your variance or your function is your parameter is your parameter have a sigma square, right? For example, right, just now we have the normal is usually you have your variance is sigma square, right? So usually we don't try not to use sigma square as your parameter, because you have a square, then you might square root. Is a bit difficult, right? Because your square root can be negative, positive, whatever, right? So that's why people will write your sigma square as a phi here, right? Instead of using sigma square, we use phi. So phi is like one parameter, it's not sigma power 2, right? To avoid confusion. Okay, so anyway, phi is actually sigma square. So now you have your likelihood for your phi. Okay, so if you then you have your transformation, right? Which is your, I always don't know what to call this. This is your eta. Yeah, I just use eta, I guess. Eta is the log of 1 minus phi. Okay, which is actually minus log phi. Okay, and then if you do the inverse, is actually phi equals to exponential minus eta. Okay, then we will find the likelihood for eta now instead of your phi. Okay, because if you look at the likelihood for your phi, right, it's just a phi power exponential something, so it does not really imply anything. But if you use the transformation, you have from phi to eta, right, then you use transformation. I think exponential. Right, so yeah, it actually involve a lot of writing. Okay, now you have your after transformation, right? And then remember, right, your likelihood is invariant. So now to transformation. So that's why you have your phi, you change to exponential minus eta. So that's why you get this. Okay, and then this, if you join the exponential, right, you have this function. Okay, so now what happened is actually you have to play around, right? So our aim here is actually to show that it's actually data translated likelihood. Okay, so if you have a data, so you want to have a function of, so now your parameter is your eta, so you must be eta minus your t sufficiency t something, right? So it's a function of that. So this will actually involve certain, not tricks lah, but certain maneuvering, right? So you have this, right? And then you have exponential x squared plus bracket. Okay, so now what happens here is you can see, right? Okay, so now I want to have a function, right, of what I call it, of eta, and then a function of my data. So now my data actually is only my y is only in my s square, right? My s square is this function. So my data is only in my s square, right? So then the idea is you need to do something, right? And so yeah, now this is actually your what call it, your sufficiency statistic. Okay, so then okay, so if we were to define our t as minus log s square. Okay, we want to define this. So then, okay, this also involve more maneuvering, right? You know, we add things, minus eta minus t. So t is your ty, okay? Bracket. Wait, oh, I have bracket, too much bracket. Okay, so this is technique, right? Where, okay, so now because you want to show there are data translated, right? So remember, right, for data translated, the function, right, the function must be g theta, or in this case eta, right? It must be eta minus t. T is your sufficiency statistic. Okay, your sufficiency statistic, right? Then you have your, that's why, so if your t is your sufficiency statistic, so now it's a minus log s square, right? So you actually have to add, because if we want to have a function in eta minus t here, so we put we add minus t here, right? So this one is already from here, this is already eta minus t, right? Because it's minus here. So this one is already eta minus t, because exponential eta minus t here is already there. So here we have to add in your t here. Okay, you have to add in minus t here. So minus t here, you have to add in minus t here. Okay, so that means that you have to add in here, right? So this one is because minus t here is actually exponential, right? Exponential n over 2, right? So you minus here, you add here. That's why you have additional here, right? Okay, but because it's the t is from the data, is a constant, right? So actually this is proportional to your exponential gamma minus t. Okay, and you have exponential gamma minus t here. Okay, bracket. Okay, so that's why actually you get a function. So you can see here it's actually a function in eta minus t. Okay, and so if you were to write it as a function of x, then it will be a exponential n minus 2, which is x minus exponential x. Okay, right? So this, now you can see that this is actually the likelihood of the eta is actually a data translated likelihood. Okay, so this means that this is why it implies that if you want to choose a prior for your eta, then you can actually use a flat prior. Okay. Okay, although a flat prior for, just remember, a flat prior for eta actually is not a flat prior for phi actually. So this one is actually 1/phi. But this one is just side. Okay, so this means that if you were to look at the phi originally, right, it does not imply a data translated likelihood. Okay, but with transformation and a lot of algebra, okay, you can actually show that if you use this transformation, your eta, after you transform your variance phi to eta, right, then you can actually show that the likelihood for your eta is actually a data-driven. So it is actually a data-driven likelihood. So that will imply that you can actually use a flat prior for your phi. For your eta. Okay. So this means there's another way. So sometimes in one form, the parameter does not have any certain special characteristic, but with transformation, sometimes the parameter will change and will have a certain characteristic that will imply you to use some prior which is you think suitable for the data. Okay. Right. What time is it? Okay. Right. I think oh, right. Okay. I think we have a bit of time. Okay, so the next one. Oh, okay. I think the next one will actually be long because you have to explain. Oh, all right. So maybe we have some time. Okay. So the Jeffreys prior. Okay. So basically this chapter is all about talking about different priors that you can use. Okay. So one other kind of priors that we can use is called the Jeffreys prior, which is based on the Fisher information matrix. Okay, and if you can see over here, is actually you have to differentiate the log of the likelihood. Okay, either you double, you differentiate twice, or you differentiate once and power 2, and you find the expectation of the log likelihood, and then you get this is the Fisher information. Okay, and the Jeffreys prior is based on is proportional to the Fisher information matrix, but square root of power 1/2. Okay, and it is often used as a reference prior also because it actually has the property of invariance under reparameterization. Okay, meaning that under transformation, the reference prior for theta and the reference prior for phi are, the reference prior for theta is still the reference prior for phi. Okay, this is what we mean by property of invariance. Okay, so if you look over here, okay, then we have the Jeffreys prior for phi. So we have, first we have a transformation for phi. So phi is actually a function of theta. So originally we have a parameter theta, then you have phi is a transformation or function of theta. Okay, and then if you look at the phi, the Fisher information for phi, right? So this is the definition for Fisher equation for phi, right? And if you look at the phi is actually transformation of your data, right? So you have the log theta here, and then you have the Jacobian, right? Okay, and then you can take out this, and then you have this. So this is actually the Jeffrey, the what you call it, the Fisher information for theta. Okay, and if you multiply, if you want to find the Jeffrey prior for theta, sorry, if you want to find the Jeffrey prior for phi, sorry, Jeffrey prior for phi, then it's just the Fisher information. So it's actually the Fisher information for theta multiplied by the Jacobian, then you actually get the Jeffrey prior for phi. Okay, so this means, as I say, right, this means that Jeffrey's prior for theta is still the Jeffrey's prior for phi. So it's not the same, it's equivalent, right? So meaning that if you have the theta, right, and then you transform it to phi, so the Jeffrey's prior for theta still imply Jeffrey prior for phi. Okay, what this is meant by equivalent. Okay, so meaning that if I were to change my theta, I would just transform my theta to any other parameterization, I will still get, if I want to use Jeffrey prior, then it's still Jeffrey prior for any other transformation. Okay, I mean, the Jeffrey prior means it's not the same PDF, but it means the same definition. I mean, this one, right? This definition for Jeffrey prior. So if I change my theta to phi, this formula still applies to any other transformation of my theta. Okay, I still have to find Fisher's information and then square root. So this means if I change my theta to phi, I still use the same notation or the same formula to find Jeffrey prior for phi also. Okay, right. So maybe we can look at example if we have time. Okay, right. So before we stop. Okay. All right. Okay, so we have Jeffrey's prior. Okay, so now we have Jeffrey's prior for binomial. Right, so remember, right, binomial, so you have your likelihood for your binomial. Okay. Then you have your, because now you have to find the Fisher information. So your log likelihood, right? Yeah, so you need actually a lot of statistic, right? Because you have to differentiate and integrate. Okay, so you have your log likelihood. Then you differentiate your log. We differentiate against your log L, log likelihood. Right, so you have this. Okay, and you differentiate twice. Okay, then you have to find your Fisher information. Right, for Fisher information is you have to find the expectation. Okay, so expectation against your Y, which is the distribution of your Y. Okay, so why is this distribution Y is important? Because here your Y is binomial, right? So this Y is, you must have a distribution here. Y is a binomial and theta means the mean is n theta and the variance is n theta y minus theta. So that's why you have to, the efficient is the expression of this against your Y, right? So if you look over here, if you look at this log L after you differentiate twice, you can see here, okay, for in this case, right, if you, because you expectation against y, means that in this case, your theta is a constant. So the expectation is only against your y. So you have minus, right? So that's why you have y here. So that's why it's important, right? When you find expectation is against what, right? It's against, here is against y. So y is large. Okay, so here theta is a constant here, right? Okay, so whenever you do this sort of thing, your all this formulation, you have to check like what is the constant, what is the variable. So here, if when you do this expectation against y, it means that y is your random variable, and here theta is a constant for this case, right? For this expectation. Okay, so that's why your y here expectation here, right? And you have this, and theta square is constant. Okay, and then the expectation of y, this is where you have to find the distribution of y is binomial. So the mean, right, the expectation of y is actually your n theta, right? Okay, that's why expectation against y, then you get your mean expectation of y is n theta. And then you have n theta again. Okay, and then you simplify. Okay, so here, what happened here is, right, you can take out your n, right? And you can actually not simplify, you can actually rewrite. In this case, you have, this is actually, you can rewrite in this way, and you can actually get this. Okay, so you multiply and then you take out your n, and you can actually get this. Okay, right. Why is this important, right? Because it looks like a beta kernel. Hint, right? It's a hint. So you have your p theta is actually your Jacobian, your Fisher information power 1/2, which is actually proportional to this. Okay, so this is actually a beta kernel with parameter 1/2. Okay, so that's why from here you actually have this form, because it's easier to look at when you have the same kernel, right? Okay, and then your posterior is actually beta, wait, the right, your posterior is going to be a beta this, wait, I think, okay, I think we have to stop. Actually, this one I haven't finished yet, the example, but I think because it's 7:15 now, we have to stop now. Okay, and I'll continue after the break, which is